Hello, welcome to my talk on Reynolds number and turbulence boundary layer modeling. In this talk, I will answer some important questions for the turbulent boundary layer modeling, including CFD boundary layer modeling. These questions include how to assess the wall shear stress when we only have the basic input for the modeling. What is the turbulent boundary layer thickness and how many wall units in the boundary layer, and how to build the grid for a good CFD simulation so that we can resolve all regions in the flow field, especially the near wall regions. Although differences in the boundary layers in different flows, by using the similarity method, we can still find the common features of the flow boundary layers. The classic boundary layer is that we can see in many textbooks and articles. See this plot. Generally, for the boundary layer, we have 4 different layers. The layer close to the wall called sublayer, and above that there is a thin layer called buffer layer. And then we have rock roll layer, and the outermost layer called the defect layer. For mathematical representation of the boundary layer, we can define some important parameters, such as the friction velocity u tau, defined as this expression. Here, rho is the fluid density and Tw is the shear stress on the wall, which is essentially unknown before the problem solution. However, in solving the fluid problem, we might need to know what is the friction velocity. There will be a catch here, how we can calculate this if we don't know the answer yet. In the next few slides, I will talk how we can obtain the shear stress on the wall Tw. And based on the friction velocity, we can define 2 important non-dimensional parameters. The first one is the non-dimensional velocity in the boundary layer, defined as u plus, equaling u divided by u tau, the friction velocity. And the non-dimensional distance from the wall surface, or called wall unit y plus, given by this expression. From the expression, we can see y plus has the same expression as the Reynolds number. Here, the velocity is the friction velocity and the length is the distance y. And using the similarity method, we can obtain the logarithmic law given by this expression. So this expression is generally valid for the wall unit y plus larger than 30, and the constant c is generally taken between 5.0 to 5.5 based on the reference 2. And we also have the viscous sublayer, which is given by the expression u plus equaling to y plus, when y plus is equal or less than 5. So we can see in the drawing, the straight line here is the logarithmic law, and here is the viscous sublayer. So we can see these expressions can well represent the boundary layer. In the reference 1, Ding compared a dark flow, see this picture, and the pipe flow based on the Blasius skin friction law, and he found that his formula is very close to that Blasius obtained for the pipe flow. When we compare this and this, the slight difference is the coefficient 0.073 and 0.079. And the Reynolds number here is based on the mean velocity C here. So as this result, the recommended formula for the friction coefficient is given, CF, as this for the duct flow. And also, if we look at the book, reference 2, the universal dimensionless mean velocity profile of the turbulent flow are all very close for the data from the pipe flow, the channel flow, and the boundary layer measurement. So in this regard, the recommended formula can be used for calculating the wall shear stress. Then, further analysis the skin friction on the 2D rectangular duct flow. Instead, use the mean velocity. Here, he used the velocity at the center of the duct. So he get the friction coefficient for the duct flow given in this formula. Here, U0 is the velocity at the duct center line, and Reynolds number is defined as based on the mean velocity of the duct flow, U bar, and the duct height, H. So based on the friction coefficient, we can easily calculate the surface shear stress given by this. This formula was used in the DNS, Direct Numeric Simulation Modeling, in the reference 2. This used for calculating the friction velocity in the duct flow. So for calculating the wall unit for the DNS modeling grading. In the cases of general applications, we may apply the following expressions from the reference 1 here. For the internal flow, the friction coefficient CF is given by this formula. This is actually the Blasius skin friction law. Here, Reynolds number is based on the free stream velocity U0 and the pipe diameter D. And for general external flow, the friction coefficient can be calculated using this formula. And here, the Reynolds number is called local Reynolds number, which is based on the free stream velocity U0 and the horizontal distance x. So once we have the friction coefficient CF, then we can calculate the wall shear stress given by this. Then we can calculate the friction velocity U tau given by this formula. And we can then calculate the wall unit, the long-dimensional wall distance, Y plus, given by this expression. Here, Y is the vertical distance from the wall. In here, we examine an example to see how we can assess the wall shear stress, the turbulent boundary layer thickness, and the total wall unit in the boundary layer based on the relevant flow condition. That is, the flow Reynolds number. It should be noted that the example is for showing how we can carry out the relevant assessment. And we will see some of the calculated parameters would not only depend on the Reynolds number, but also on the free stream velocity and thus the horizontal distance. Here, the example is the flow past the flat plate. See the plot. And the turbulent boundary layer happens at local Reynolds number larger than 500,000. Assume an air free stream velocity is 100 meters per second at 20 degrees. Now we want to calculate the wall unit in the boundary layer. In the problem analysis, this example can be regarded as an external flow, and at 20 degrees, the air kinematic viscosity nu is 14.88 times 10 power of minus 6 meters squared per second. And the air density rho is given as 1.204 kg per cubic meter, and the free stream velocity U0 is 100 meters per second. So the first step is to decide the critical horizontal distance x1 based on the critical Reynolds number calculated by this. So we have x1 calculate as this. Here, from the leading edge to the point, the turbulent boundary layer occurs. And for x larger than 0.0744 meter, the boundary layer would be turbulent, and the local Reynolds number Rex is calculated by this formula. And if we draw the distance and the Reynolds number, we can see Reynolds number in this case is linear proportional to the distance x. See this plot, the straight line. And from the recommendation, we can obtain the friction coefficient Cf given by this expression for the external flow. And then we can calculate the wall shear stress tau W given by this expression. The friction velocity U tau given by this. We can see the friction velocity is dependent on the free stream velocity U0 and the Reynolds number here. Now for calculating the boundary layer thickness delta, we can, based on the Prandtl's 1/7 power law, see this comparison. When the Reynolds number Rx is from 100,000 to 10 million, the Prandtl's 1/7 power law would be very close to the actual boundary layer profile. And based on the Prandtl's 1/7 power law, we can obtain the boundary layer thickness delta given by this. So we can see here the boundary layer thickness is proportional to x and depending on the Reynolds number. And then we can calculate the wall unit y plus for the whole boundary layer. So the calculation would be given as this. The velocity is U tau, and the length is the boundary layer thickness delta. So we have the expression for the wall units for this example given by this. So we can see the wall unit is only depend on Reynolds number. And also we can calculate the unit wall distance. This is for y plus equally 1, so delta y1 given by this expression. So based on all this expression for different Reynolds number from 1 million to 50 million, we can see the boundary layer thickness is increasing with the Reynolds number. And the unit wall distance delta y1 is increasing as well. Here we notice the unit wall distance delta y1 in this example is from 3.5 to 5 micrometers. So these are very small distance. and the number of the wall units N is increasing very fast. So this is the plot for the boundary layer thickness against the Reynolds number. The larger the local Reynolds number, the thicker of the boundary layer. And the unit wall distance delta Y1 is depend on the local Reynolds number REX, but not very much like the strong dependence as the boundary layer thickness. This is the wall unit N against the Reynolds number. So we can see the larger the Reynolds number, the more wall units in the boundary layer. When the Reynolds number from 1 million to 50 million, we can see the huge increase in the wall units. From this example, we can see the number of wall units in the turbulent boundary layer can change dramatically with the Reynolds number. This is why people don't like to tell how many wall units in the boundary layer. Hope this example can give you some idea of the turbulent boundary layer thickness and the wall unit. In this slide, I will show how we can generate the grid for the turbulent boundary layer. Following the ANSYS Fluent, we can see two different approaches would be used for modeling the flow in the near wall region. See this plot. And this principle is the same for many other CFD simulations when dealing with the near wall regions. The first approach is employing the wall function. As such, in the near wall region, including the buffer and the sublayer near the wall is bridged using the wall function, such that coarse grid near wall can be used, and high Reynolds number turbulence models can be used only for this type of flow simulation. See this part of the drawing. The second approach is the near wall modeling approach, in which all regions are resolved down to the wall. Thus, the very fine grid must be used in the near wall region. See this fine grid here. Also, low Reynolds number turbulence models must be used in the near wall region. Take an example, Reynolds number 1 million from the previous example. The boundary layer thickness is 3.5 mm and the delta Y1 is 3.5 micrometers. Following the suggestion by Spallard, we have the expression for generating the grid by this equation. So we can obtain N equaling to 28. That means within the boundary layer 3.5 mm, we need to generate 28 grid for the near wall modeling. So we can see the very fine grid must be generated near the wall. So this will apply the challenges for the near wall modeling approach in the practical problems.